disclaimer. You might want to change your major to aerospace after this session.
All right. So today we're gonna start with flight computer and software. So let's begin. What do we need our flight computer to actually do? So when we actually go into the launch site, we get at least 40-50 feet away from the place where we actually launch rocket. And so we want something that could trigger the launch itself. We press some button and it triggers the launch, and we want our flight computer to actually record all of the data. So it's highly likely that our initial rockets might not work as the way we want them to. So to see actually what went wrong and to come back later and correct the mistakes, we actually need data. We need to see in the data that, oh, okay, so the thrust here was not enough, or how did our trajectory of a rocket, how did the orientation of our rocket change over time. So we actually record all of the data in real time in our flight computer, so that we can study that later, study the performance of our rocket. And how will we know that how high did our rocket actually go? So we use sensors to see the real time height. We can also transmit the data in real time. That is called telemetry. We can use radio communication to do that and stuff like that. So, and we also want that at the highest point, or a few seconds after the highest point, uh, our parachute gets ejected so that our rocket could be recovered, so that we don't have to do it all again. We can actually use the same hardware. Now, how to actually eject the parachutes? So we can actually use some reliable spring-loaded mechanism. Like if you remember, the parachute is actually stored in the upper section of a rocket, and the nose cone of a rocket could be popped up, and we fold our parachute and put it inside the nose cone. So nose cone could be popped up. It's like the cap of a bottle. Now you can either use a spring-loaded mechanism like this. Here, it's instead of spring, they're using rubber bands. Uh, so what's happening here is that these rubber bands are holding these gates, which could actually flip open, but they cannot flip open if they are inside this casing. So this is one of the many possibles. This is one of the many possible designs that you could do with springs or rubber bands. So as soon as this pink wire loop is detached by rotating the servo motor, this this entire system gets free, and these rubber band actually shoot up this entire thing, which includes the nose cone and the parachute housing. And then the parachute can open because these gates are free to open and actually spring loaded. So they want to open because of these spring systems right here. Now we could actually make a spring loaded mechanism like that, or we can use pyro charges in the nose cone. So what are our pyro charges exactly? It's the black powder, it's the gunpowder, which we ignite using electricity. We send high amounts of current, which increases the temperature to the ignition temperature of that black powder, and that ignites our black powder. And because this entire casing is almost airtight, so the pressure inside, so as soon as your black powder burns, it releases a lot of carbon dioxide, and that carbon dioxide actually pushes and pops this nose cone pretty aggressively. And we need this entire thing to open up aggressively, otherwise uh, our parachute, this cord of our parachute will not be stretched enough to open up, and it's going to be entangled within itself. We want it to shoot out as fast as possible. So we actually use electrical power to ignite the pyrocharges. Now, our flight computer actually runs on something like Arduino or something. Our flight computer is basically some microcontroller that runs on voltages between 3.5 volts to 5 volts, or max 9 volts. So that voltage is insufficient. That cannot provide that much current. And if so much current pass through your microcontroller, it's gonna cook your microcontroller up. You have to use a different one then. It's gonna be cooked permanently. You cannot fix that. So how do we actually control a lot of current with something like our microcontroller, which cannot run on a lot of current? So we use something called MOSFET. So we have a powerful lithium polymer battery as an external battery. We draw current from that battery, and we control the circuit of pyrocharges and that external battery using a switch called MOSFET. and that MOSFET could be controlled by our microcontroller or our flight computer. So indirectly, we control the amount of current going into our pyro charges. And as you can see that this is how the ignition charge plug looks like. In the top, there's black powder. This is a plastic sleeve that actually bursts open, and this is the nichrome wire that actually acts as an igniter. We pass high currents through it. So similarly, we ignite our rocket motor. So we when we launch our rocket, we use some igniters, rocket model, rocket igniters. As you can see, this is how the igniters actually look like. They're pretty cheap. Um, so as you can see that this caught fire, and this actually burns our this actually starts the ignition of our rocket motor, and it burns the rest on itself. Once I'm walking you through all of the required knowledge, and once you have this knowledge of model rocketry, we can finally write the software, and it's just gonna take a couple more minutes. Now, how do we actually store the data recorded by sensors live within our flight computer? So on boards like Arduino Uno, we have little to no memory on board. So you have to use some external source of memory. For example, SD cards or flash memory chips. They are SMD components, surface mounted components. They are pretty small, uh, soldered on the green PCBs. So by default, it has just 2 KB of SRAM and 1 KB of EEPROM. So SRAM is static random access memory. It's kind of like RAM. It is volatile. It is a form of volatile memory. That means as soon as your Arduino is powered off, the memory is vanished. The memory is no longer there. But this EEPROM is actually like ROM. That is read-only memory, kind of like our HDDs, hard disk drives. Uh, but it is only 1 KB, so it's kind of useless. And so we'll discuss that how can we externally connect the SD cards and flash memory chips to our microcontrollers. We're going to actually do that today. Now, voltage regulators. So what happens is the battery that you're using is not perfect. So the voltage that is coming from your battery is not going to be perfect. So you actually use a voltage regulator that can increase or decrease the voltage using some kind of transformer, a small transformer inside it. That is step up or step down your voltage. And then there's some smoothener at the end of your voltage regulator. So if there are little fluctuations in your voltage, that can actually harm your microcontroller. So you need to input a smooth power voltage. So what you can do to do that is the simplest form of voltage regulator is if you connect your input voltage to the ground with a capacitor in between, like this. So this is your positive end, this is your negative end. If you have a capacitor in between them, and the rest of your circuit connects after this, so what's going to happen is in case when the voltage fluctuates higher than usual, the charge on your capacitor, the momentarily charge stored in capacitor, is going to increase, because if the voltage increases, then your capacitor have chance to store extra charges. So instead of those extra charges going into your circuit and fluctuating the current, it's going to store into your capacitor. And in cases when your voltage fluctuates downwards, that is lower than usual, your capacitor actually flows the charge stored on itself into the circuit so that the current doesn't fluctuates down. So this smoothens out your signal. So for example, this is AC, that is alternating current. It's alternating between positive and negative. You pass it through a rectifier circuit. It becomes only DC. It becomes DC, varying DC. That is only positives. And then you apply the smoothing that I was talking about, like this. So as soon as your voltage will be increasing, your capacitor will actually charge. It will pull charge on itself. And as soon as your voltage starts to decrease, the charge on the capacitor runs into the circuit and stops the current from dropping too much. So this actually smoothens out the voltage input over time. I'm gonna introduce you Autodesk Eagle PCB. So if you remember, we discussed PCB in our previous session, where we discussed that why do we actually need PCBs? How does the cross section of PCB looks like? That is, it's just basically insulator layer with copper traces on it for the connectivity, and we can solder. We can physically melt some conducting metal to connect components to it. So it is a pretty pretty reliable connection, unlike wires on a breadboard. Now, in Autodesk Eagle, the process of designing a PCB is like this. So when we start designing our own flight computer, you have the list of parts, that which components, which sensors, and which microcontroller are you using, which memory are you using. Now you lay down all of those components in your Autodesk Eagles library. If you don't have those components in pre-existing library, you create your own library. It's kind of easy. I'll tell you about it in a couple of seconds. Now, then, as I told you that there's something called schematic diagram from our previous session, if you remember. So this is how a schematic diagram looks like, a simplified version of your circuit. And then there's placing all the components on the board. So there's a schematic diagram. Let me show you. If you have the software on your systems, please open it right now. So this is the default view when you open your software Eagle. So here you can see that we have projects. We have the libraries available here, pre-made libraries. For example, this one. These are the libraries made by Eagle. I mean, like organized by Eagle by default. So you're gonna find the all of these libraries by default. But you can add more libraries on top. There's an entire library manager, which is like the browser for the libraries. You can directly go and download libraries from there, or you can go to Google and just search for the libraries on, like, some people make pretty good libraries for different components that you won't find in either of them. Go into project and create a new project like that. Right click on projects, and so let's name that session 6 flight computer. Now you can do two things. In this project, you can create a schematic or a board. So schematic is the schematic diagram that we just talked about. On the other hand, the board, or you can create a new board view. So if you're gonna do board view, you'll see something like this.
Can you show me again? I'm kind of lost.
I don't know why the hell is this not letting me. Okay, no. All right. So as I was saying that if you're gonna right click on projects, you're gonna
Yeah,
see.
I did that. New project. Okay.
then then if you're going to right click on your new project, then you can see that you can create three things: a schematic, a board, and a library, and a couple more things. But we're going to first make the schematic, because remember, the schematic is the most simplified version of our circuit. If we have something to start with, that's the thing that we'll do first. So if you're going to click on that, you will see a window like this.
I clicked on new project, but it just keeps creating a new project.
Let's say hover your cursor over new project 2.
Mm,
Put a right click, just a single right click. Can you see that drop down?
no,
You cannot.
it only shows like open project and all that. Rename, copy.
That's kind of a bug. Uh, can you double click on your project? Right click on the
Nope.
eagle icon. Right click on the eagle icon.
Oh,
Okay.
there you go.
If you open the schematic view, you will be able to see this kind of window.
Mm,
Here you can add, you can start adding the components from here. Add part. If you're gonna click
okay.
on add part, you will see all of the parts
Actor.
available in all of your libraries.
Uh-huh.
But so right now we have to think that which kind of flight computer should we make. So let's start with very basics. Let's do one thing at a time. So let's actually add the microcontroller that is actually on the Arduino, but we're gonna make our own. We're gonna make kind of our own Arduino which can actually handle flights. So if you're gonna search Arduino here and then enter. Uh, I am actually seeing these because I have installed this library, but can you share your screen and search? Because you are not gonna see any
Yeah,
of these,
I'm not seeing anything.
right?
Yeah. Okay.
Now open the library manager.
Yeah.
Now, if you're gonna go in available tab, this is kind of like the browser that I was talking about. So these are the
Mm-hmm.
libraries on internet, not on your PC right now. So you can
Mm-hmm.
actually search for Spark Fun, SPARKFUN. Now,
Spark fun.
yeah, increase the width of the name column.
Hmm.
Now you should be able to see the libraries made by SparkFun. So actually, SparkFun is a manufacturer who actually manufactures most of the sensors we are actually going to use in our rockets. There are two main companies, that is SparkFun and Adafruit, ADAFRUIT. So let's go with SparkFun's library. Can you see microcontroller?
Yeah.
Just download this library.
Is it done?
Yeah, it is. As you can see on the bottom, so it say moved this library
Mm-hmm.
to in use. So it is in
Yeah.
use tab now. It is done. Now actually download a couple more libraries from there. Spark Fun Sensors.
Sensors. Yeah.
Yeah, please download that too.
Hmm.
And we can actually use most of their stuff. Like we can use their GPS. We are just gonna go with sensors and microcontrollers right now.
Okay.
Now search. Now close this library manager. Yeah, now you will be able to search Arduino. Okay.
Yeah.
Increase the column width of name column. Now, as you can see that it says at mega 32 U4, right?
Mm-hmm. Hmm.
That is one of the chips, that is one of the microcontrollers that comes in one of the Arduino. Now, if you're gonna click on the drop down, so these are the different variations. Close this library manager, search Arduino. As you can see on the right hand side, uh,
Mm-hmm.
the preview of these chips.
Yeah.
So it depends which one do you want to use. Let's go with the first one. Okay. And then just add this by doing a single left click. Actually, if you just keep clicking, it's gonna keep adding. So just click once. Now, let's interface this chip. This is the bare chip that was on our
Hey.
Arduino,
Sorry. Can you repeat which one to click?
the first one.
This one.
Yes, yes, this one. Okay, press OK. Now just do a single left click. Yeah, now you're done. Now click on add parts again. Now let's search for what do you do? What do you want to do first? A sensor, like a temperature sensor or something, or
Yeah. Let's do sensors.
sensors, right? So okay, let's go with an accelerometer. That accelerometer could actually tell. So a rocket. Imagine that a rocket is standing on our launch pad. So the acceleration is 0 right now. Imagine now acceleration. Now there's some value of acceleration along x, y, and z axis. Now you can integrate that acceleration over time to get the velocity, and then you can integrate that velocity over time to get the displacement. So just by an accelerometer, you can tell that where your rocket is right now, and by using by using gyroscopes, I mean the the sensors that measures the angular acceleration, that how fast is your angular velocity changing. Using those sensors, we can see that how is our rocket actually rotating. You can do the same integration twice with time, and then you can get the angular displacement. How much did our rocket rotate in total? So that way you're gonna get your attitude. There's a term called attitude in aerospace industry, which is actually used to describe where is your aircraft or spacecraft pointing, which is the orientation. It's just a different word used for orientation. Now, if you're gonna search for accelerometer, you're gonna see a couple of these sensors, but we don't want to use them. What we actually want to use is MPU. 6050. When you will search that, you will see nothing because it is not available. If you search MPU, still there's nothing. So this library manager is of no use right now. Spark Fun. Even when we had the sensor library, MPU 6050 is not covered in that, right? So now I'll show you how to create your own library. 6050. You'll see these breakout boards, right? So is it better to use this bare sensor, that is the small black chip on the on this breakout board, or is it better for us to use this entire breakout board? What do you think?
To use Interboard.
Yeah, entire board, because there's a lot of pre-processing on the raw signal that is being implemented on that board. If we are not going to use that board, we have to do it all by ourselves. So to be
Mm-hmm.
quick and to save a lot of hard work, we're just going to use that. So if you can open that to see how what are the dimensions of this and how are the pins arranged, you can actually make your own library inside Eagle and putting all of this information. So this is also called GY521. Let's see the dimensions. Naming of different sensors chips is kind of confusing, so just consider this as an accelerometer gyroscope. So its description, you can see its description written on these websites. Or what I like to do is just type datasheet in front of that sensor or whatever you're looking for, and then the actual datasheet that I was discussing about in the last session is gonna pull up where you can see the dimensions, package dimensions. So as you can see here, here are the dimensions. So it's 21.2 millimeter in length and 16.4 millimeter in width. Now let's just open Eagle again. We're gonna do the same. Right click on our project and then click on new. We this time we want to make a new library. Click on library. A window like this will pop up. Click on symbol. So what we just added in our schematic is called symbol of that chip. It's not the actual chip. It's not how actual chip looks like. It's just the symbol of the chip. Just for example, this kind of symbol zigzag is the symbol of resistor, if you remember. Now we're gonna first make the symbol of that sensor that we want to make. We're just gonna name this GY521. You can do this with me. Are you just
Where's the
click on
symbols? Yeah,
this
symbols.
this plug light new symbol here, right?
This one.
Yes, yes.
Yeah.
Click on it. Yeah, now name your new symbol as GY521. Click OK. Yes. Now, all right. So here we're just gonna do a rough sketch. So what should be included in a rough sketch? So out of all of this information about this sensor, uh, there should be that what pins are there on the sensor. So we're just gonna make any rough diagram kind of. Click on the line, do it like this, any rectangle, and then after rectangle, click on pin. Now you can add pins. So by default, your pins are gonna be oriented horizontally. But if you're gonna right click, then your pins are gonna get vertical. Now you can add those pins. How many pins were there? 1, 2, 3, 4, 5, 6, 7, 8. So there are total 8 pins. 1, 2, 3, 4, 5, 6. Okay, let me just make it a little wider. I'm gonna go online again. I'm gonna go and pin, do the right click to make it vertical, and then just add these pins. 8. So there are 8 pins now. Now what you can do is press escape so that so that the pin adding option is no longer on your cursor. Now you can right click on these green circles and rename them accordingly. So the first pin should be VCC, just like this. Rename all of these pins, G and D, SCL, SDA, XDA, XCL, add int. Or instead of again doing the right click on these green pins, you can do one thing. Just select on this tool, and then wherever you
Uh,
click, it'll rename it.
I'm stuck.
Okay, so the problem is your grid right now. Let me guide you. Open your ego.
Hmm.
Uh, just undo whatever you did.
I think I found it.
Oh yeah, you had just too much zoomed out, right? Yeah.
Yeah, yeah, yeah.
Okay,
Okay.
that why your line was that thin. I
Hmm.
assumed that, but then I was like, but the grid should still be visible. But never mind. All right, so locate that cursor, that plus symbol that comes up. You can hit Control Z to undo your mistakes.
Is
Yeah, good enough. Now go on.
oh shit.
It's gonna look that it's still creating a line, but it doesn't create until you hit your left
Hmm.
mouse button. So go on the plus symbol on the left toolbar. No, on the left toolbar. This green plus.
Wait. Oh.
Okay, let me show you this symbol
Hmm.
to add pins.
Yeah.
All right, so the pin is oriented horizontally right now. Do a
Hmm.
right click on your mouse. So it's now vertically oriented. Now start
Yeah.
putting pins from left to right, not from the top
How many?
to the bottom. Pins
Okay.
should lie outside the body. Start placing the pins. See that how many pins are there in this. See my screen right now. There are
Three, four,
8
five,
pins.
6, 7, 8. Okay.
Yes, place 8 pins.
Hmm.
Yeah. Now you can hit escape key. Now it's gone, right? So now you can
Yeah.
click on this R2 from the toolbar again. The left side is called toolbar. There are all the tools available. Click on R2. This is for rename. Now you can click on any green part of the pin. It is selected. Now you can click on any, yeah. Now you can rename them.
Yeah. What's the first
Rename
name?
them accordingly. VCC, GND, SCL, SCL.
G. Yeah. SEO, SEO.
All right. Now this is the symbol of our gyroscope and accelerometer sensor. Now
Hmm.
we're gonna save this as a just hit Control S to save that.
Gyro.
All right. Now the symbol is created. Now we have to create the board. How does it actually look like? The original dimensions. So for that, I mean that is called footprint. So add footprint. Name the footprint GY 521 again. Yes, I want to create it. You'll see a window like this. Not here, not here. Near this window. Yeah. Add footprint on the bottom. No, on the bottom.
Okay.
Yes. No. So now you can add a description of your sensor right here. So for example, you can just say that MPU 6050 And in description, you can also include the dimensions of your board. So I'm just copy from here. I'm gonna paste it. I'll also paste on the Discord so that you can use it. Now I'm gonna click OK to save this description. All right. You should also type MPU 6050 in front of this
Oh yeah,
description. Just click on yeah
MPU
6050.
6050.
So these are dimensions, right? 21.2 mm and 16.4 mm. So we're just gonna make a rectangle of this dimension, and we don't care about height right now. Okay, from this tool, dimension. So we're just gonna click here on the dimension tool, and we can actually draw a line like this, 21.59. This much tolerance will be fine. This is 21.59 millimeters wide. That's gonna be okay. You can just double click so that this is saved. Yep, 21.59 on the next. Yes, double click.
Then the height, right?
Yes, as close as 16.4 as you can get. Now click on the line tool and draw the rectangle. Now when the rectangle is done, click on pad. These are the holes that you see in this diagram right here. What's the distance between these pads? They are basically equidistant to my eyes. Let me try to do that. 1, 2, 3, 4, 5, 6, 7, 8. I guess this is correct. We can select which kind of hole we actually want to make. So there are different type of pads on a PCB, as you would have seen by your eyes as well. So actually, I'm gonna start doing the holes from these circular holes, right? So let's select circular holes.
Okay, it's kind of unsymmetrical.
We can try changing our grid size. Okay, this seems correct. Yeah, this is now correct. Okay, change your grid sizing from 50 to 25. Click on the grid. Yes, 25. So basically what you're doing like this is you're bifurcating every single square on your grid into half. I guess you right. Your rectangle is not complete. These are just the arrows. These are not real
Oh
lines.
yeah.
Yes. Now just click on the pads, the green button, the green option in the toolbar, and place these pads symmetrically.
Yeah.
You got it?
Hmm.
Okay. So now we're gonna save it. Hit Command S. Now you can just close this, and
Saved, right?
yeah, you'll be able to see your footprint. So we just made this footprint, right? We placed the pads on the footprints. Dimension wise, it looks exactly like this. One thing we skipped, that is the holes. We'll talk about holes in a bit later. We can just come back again and fix this. Oh, we missed one thing. You can just edit your footprint again. And so, okay, so all the pins are named. Now you can also write the text. For example, you can say that this is MPU 6050 VY 521, whatever you want to say. And you can stick the name on top like that. That's gonna help you identify that what part this is in your schematic later down the line. You can also do one thing. You can delete this, delete this measurement. You don't want this in your schematic. Hit Control S and close this window. Just open your library again. Now you will be able to see your symbol. Okay, so let's also edit our symbol because we forgot to put our name on the symbol. G. You're gonna save it and close it. Open it again. Now, yeah. So now we have correct symbol and correct footprint. Now we're gonna add a device. So this is the footprint of the device. This is the symbol of the device. Now finally we can add the device itself. We're gonna name the device the same name, GY521. Yes. So this is the device window. This is the most important windows after you're done with the schematic and footprint. Here, we're going to combine both of them into a single device. If you're going to click here, add from local package, you can see the footprint that we make. And then you will also be able to add part from here, our symbol. Place this on the plus so that it's symmetric. And then press on connect. Now you will be able to see these pins on our schematic are exactly the same as footprint. So they need to be connected inside the software so that it knows what is what. So we are connecting, and this is finally becoming into our final object in our library. Now we're gonna press OK. Now this is actually done. You know, as you can see that this object is created now. Before
Hmm.
this, there was just footprint and just symbol, but there was no object. If you remember the schematic that we just started making, this is the object of this. So you can just drag and drop. Isn't that pretty cool? Like we made our own library.
Yeah.
This is your library. Drop down this.
Hmm.
Drop down the menu from left. Yes. Now you just have the symbol and footprint. There's no device, right? So you want to make a
No.
device too. So
Yeah.
right click on your library. There should be this
Mhm.
object now,
Yeah.
right?
GY51.
Now you can just drag and drop this in your Eagle, the window that we were making our flight computer in.
This one?
Yes, just drag and drop your object here. See, now you can see it, right? The main takeaway from all of this is that, for example, you browse that what are the sensors available. The sensor that you picked, you didn't find that sensor on Eagle PCB. So you
Hmm.
created your own library for that. You created your own symbol and your own footprint. Now we're gonna click on add parts. This is gonna be
Hmm.
GND. Add this ground, this one. Click OK. Place your ground anywhere. And also add a VCC. So VCC means voltage common connector. So this is the plus symbol in our battery. The plus of our battery is going to be connected to this VCC, and the negative of our battery is going to be connected to this GND.
Yeah. Okay.
All right. Now click on the net tool here, this green line. Now we're going to make the connections. So connect the VCC of your microcontroller to the VCC to give it power, and also click
The
the ground of your connect the ground of your microcontroller to the actual ground, and you're gonna see a common trait in every object, that there's a VCC and ground in every single object because nothing runs without power. Just connect the VCCs and grounds. Yeah.
that should be good, right?
Yeah,
Yeah.
for now it's good enough. Now We actually powered our microcontroller, we powered our accelerometer. Now we want to set up the communication protocol connection. So they have to share data between each other, right?
Hmm.
So for that, we need to see that what communication protocols are available on both of them. So your Arduino supports SPI, I2C, UART, all three. But your accelerometer here supports, I don't know what's the name of XCL and XDA, but it supports SCL and SDA, which is serial clock and serial data. So this is SPI, if you remember. We studied SPI yesterday, which is a serial peripheral interface. This is one of the 3 or 4 communication protocols that I taught yesterday. I mean, in the last session. So serial clock allows both of their clocks to be synced together so that they could share the data. If you remember the clock signal, that's the hard beating of both of them, basically. So they must be in the sync. So this allows their clocks to be synced. So we're gonna click on here and just match the SCL to SCL. See, this
Okay.
also says SCL. And do the same for the SDA. SDA means serial data. So the data will be transferred through this SDA wire, through this SDA connection, but the clocks will be synced through SCL connection. Do that.
Hmm. Done.
You did? Perfect.
Hmm.
So the communication protocol is now set. We just now need to program both of them. So our program is gonna go into the microcontroller, not on the gyroscope, because that is already programmed. That breakout board is already programmed. We can only program this one. So we'll also program this, but for now the connections are done, right? So let's just this session is just to introduce you, right? So let's actually like click on this icon. Yes. So you're gonna see this right here.
Hmm.
Now what I'm gonna do is click on both of them, and then move both of them to somewhere on this PCB. Select this and move it to. You can actually change the orientation like that. Now, if imagine that we had a lot of components, so that could have filled our entire space, entire PCB, right? So right now, what we're gonna do is we're gonna make these connections. So this is the insulator layer. Imagine a PCB as an insulator layer. It insulates the current. It doesn't allow the current to flow. But we draw copper paths on them, which makes which which is kind of like wires. So now we have to do those copper paths. We have to define that how this should be connected to this pin right here. You're gonna click on this route a wire tool, and you're gonna click on a pad. So you will be able to see a wire, a copper pad coming from that path. I mean, coming from that pad. So there are 4 ground connections on this chip. So you can you can use any of the grounds. You can use this ground. So this is one of our many connections. If you are not happy with how the connection looks like, just go on there again. And you can also change your grid because after this point, it's snapping to just too far ahead, right? So you can change your grid size again. Grid spacing is right here. Make it 25. Now you'll be able to get a more finer control. This is also not enough, so I'm gonna make it 12. This is fine enough. Yes. You can connect it. It's gonna snap. So this is one of our many connections that we want to do. Now let's connect the ground of this. Oops. So we did VCC and ground. Now let's do the SDA and SEL. So SDA is this one. SDA is done. Now let's do SCL. So see, here we have a pretty interesting problem. This is the last part of making PCBs. If you learn this, you'll learn everything. You don't do the connections like that.
Um,
That's gonna short circuit your microcontroller.
or I'll remove these. But show me first.
Yeah. Okay, so my point is that now I have just one connection left, technically.
Hmm,
So I could either route it like that, but it's gonna short circuit, as you can see, right?
yeah.
So this is automatically showing me another way around it, so that I could come from here and go inside and do here. But remember that this chip is already very small, and if you are not having like a good manufacturer, he cannot actually manufacture copper pads that thin and that accurately. And
Hmm,
there's a high chance of this pad actually shorting with that connection. So what instead we can do is the copper there's a lot of space in the back of this one, right? So we can actually
yeah.
go from the back from behind and connect it. This is one of the possible ways. Now imagine that there's one more connection that you need to do, and there's no way around. Like even this way is not available behind. So what can you do now? So what we do in that case is, let me show you one case. So let's say I want to connect this pin or the 16 pin, all right, to this pin, XDA. So I cannot do that because see, there is no way that I could actually connect these two. Like no direct way. This is a
Hmm,
risky way. From inside the chip, this is kind of risky. You shouldn't do that. So there's no actually good way to do that, right? So this is one of the layers on which the copper paths are being drawn, right? Now you can create this is the layer of insulator and you are drawing copper paths on them. You can create copper paths on another layer parallel to the top layer. You are actually overlapping on the same layer if you draw any connection on the same layer. So you can go underneath that connection and still
hmm.
connect them. So that's the concept of layers. So in a good PCB in Arduino, I guess there are 4 or 8 layers. Arduino board is an 8 layered board. If you're gonna zoom in with the microscope, you'll be able to see them. So modern PCBs are pretty advanced, and there are floors, like there are literally floors like a skyscraper built inside
Of
PCBs
course.
that thin. And one more thing, like just to add into that. So let me show you the actual code of that sensor. This there should be MPU. All right, here it is. So when you're gonna go to Arduino and connect our PCB to your laptop, just like you connect Arduino to your laptop. You can do it like this. Include this library wire.h and initiate this variable. If you remember in the previous session, I talked a little bit about memory and registers in the memory, right?
Hmm.
So the data from the sensor is actually stored temporarily in those registers.
Registers.
So yes, so this is the address. This is the memory address of that register. how do we know that which register to access? Every register has a unique address. So this is the address where the MPU 6050 is actually available. Now, these
It's a
are
constant
the
variable.
yes, this register is constant. Register address is not changing. It never changes. So, and these are the variables that this sensor can output to us. Acceleration along x-axis, along y-axis, along z-axis, and angular acceleration along x, y, and z. That's why it's called accelerometer and gyroscope. And
Got it.
the one that I use in my rocket also had the temperature reading, so I just included that too. Then there's a little bit more. You can actually just Google and get this code for every sensor. You can just say that um, how to interface MPU 6050 with Arduino. You're just gonna get the code and the connections. So it's pretty easy. Once you get your hands wet, it's pretty easy. Then you're gonna go here in the setup. This is the MPU 6050 sensor. I'm saying that wire dot begin, start communication between the two. Now transmission, where to do the transmission. So I put the same address, the memory address from here. I put that address in begin transmission. That start communication at from this register, right? And I said that start writing in that register one, y dot write set to 0. If everything worked till here, that means your connections are correct. Now your connection is actually activated. Now they can communicate between them. So when in the case when your MPU 6050 actually works correctly, this function is in this wire library, and transmission function is in wire library. So you're gonna this method actually returns 0 if it works properly. Otherwise, it returns the error code like 1, 2, or 3, something like that. That what error actually happened. So I'm saying that if it does not return 0, that means if it does not work properly, then please print that this sensor failed or is not present at all. So I'm just keeping in count that how many sensors failed. So I'm just increasing that variable. And I said that exit 1. So this is the exit state. This is the exit code. Like in Python, if you remember, we write break. This is kind of like
Yeah.
break, but
With C++. Okay.
yes. But instead of just breaking and leaving us clueless like in Python, it actually tells us that, oh, the error code is 1. So the person who wrote the code knows that uh, which which part exactly failed. So we can write different exit codes for different blocks of codes. So we can pinpoint that, okay, if the exit code is 1, so that part failed, right?
Mm.
So that's why it is useful. And we just interfaced all of the sensors. This is the pressure sensor barometer. This is the GPS. This is the SD card. We do it for all of them. And these are the variables initialization, different libraries. And that's how we actually put all of them in a single motherboard. That is our flight computer. So I guess you are not pretty confident that you will be able to make anything that you can think of now. At least you can learn and then make it.
Yeah.
All right. So here I conclude my session. If you have any sort of question, if you are curious about anything or from previous sessions, you can just ask.
Yeah. I'm good for now. I think I'll have to look into this more.
Sure.
32 seconds into the flight. The 3 liquid fuel main engines soon will throttle back to 72% of rated performance down in the bucket, reducing the stress on the shuttle as it goes transonic.